Previously, we spoke about interference and superposition of waves. Now we're going to examine specifically the interference and superposition of sound waves. So let's begin with the interference of sound waves in space. Let's suppose we have two loudspeakers, loudspeaker number 1 and loudspeaker number 2, each producing its own sound wave. So loudspeaker 1 produces the green sound waves and loudspeaker number 2 produces the blue sound waves. Now the green regions and the blue solid regions, solid lines, are the crests. Those regions correspond to the compression regions of our air molecules. And the regions in between the solid lines are the troughs. Those correspond to the region of expansion of the air molecules. Now, notice that eventually these two waves will interfere with one another. And so, to create the composite wave, we have to apply the principle of superposition. Now, notice at the regions where the green crest meets the blue crest, those regions are the constructive regions. That's where constructive interference takes place. So the crests meet the crest and the amplitude becomes larger. So the amplitude of the composite wave created from the superposition of these two waves is largest at this region where the crests meet the crests. Now notice where the crests meet the trough. So where the blue crest is in between these two green crests, that's where destructive interference takes place. So our amplitude is smallest in those regions. And this is known as interference of our sound waves in space. Now let's move on to interference of the sound waves in time. This creates a phenomenon known as beat frequency, as we'll see in just a moment. So let's suppose we have the following two waves, the blue wave and the red wave. Let's suppose that the maximum amplitude of each one of these waves is exactly the same. Let's suppose they begin at the same exact region and time, and so they move along the following x-axis, which corresponds to our time. Now, let's suppose that these two waves have different frequencies. The blue wave has 60 hertz and the red wave has a frequency of 40 hertz. So 60 hertz simply means that 60 cycles are made every single second, and the frequency of 40 means that 40 cycles are made every single second. So if we examine the complex wave that is produced from the interference from the superposition of these two waves, that wave is known as the composite wave. So the superposition of the two waves creates a composite wave that repeats itself every single 2t seconds, where 2t is simply the number of seconds after which the composite wave begins to repeat itself. Notice at time equal to t, the two amplitudes cancel each other, and the composite wave at this time has an amplitude of 0. Now, the sound level continuously rises and falls as our composite wave travels this way. And the period change, or the periodic change in intensity of the sound, is known as beat. So the beat is a result of the fact that there is a difference in frequency between wave number 1 and wave number 2, and we define something known as the beat frequency as the difference between the two frequencies of our two waves. So, for example, in this case, the beat frequency is simply the absolute value of 60 minus 40, so that's 20 hertz. So that means that every single second, 20 beats will be heard as a result of the movement of our composite wave. So let's look at the following example. A tuning fork produces a frequency of 60 hertz. If you struck the tuning fork and place it next to a vibrating piano string, 30 beats are counted every 6 seconds. What are the possible frequencies produced by that piano string? So our first step is to calculate what the beat frequency is. In other words, how many beats, how many cycles are heard every single second. So beat frequency is simply the number of cycles divided by time elapsed. So 30 beats or 30 cycles divided by 6 seconds gives us 5 hertz. So 5 beats are heard every single second. Now we defined the beat frequency to be the absolute value of the difference between our two frequencies. So we know that the beat frequency is 5. We know what F1 is. That's simply 600 hertz. So we have to find what F2 is. Now, two possible values for F2 fit this equation. Either F2 is equal to 605 hertz or F2 is equal to 595 hertz. So our piano string has two different possibilities for frequencies, either this frequency or this frequency. Either one works because the beat produced for both of these is 5 hertz in each case. In other words, the beat frequency is 5 beats every single second.